Hi everyone, so this is a video about a new project that I want to record while doing. So I'm going to try to implement a Lisp language. So in this video we're going to show the tooling that we use for this project. So I'm going to use NeoVim. I'm going to use my VPS where I will store the code. And in order to use my Vim environment on a remote storage, I'm going to use SSHFS. And that's it. I'm also going to set up my GitHub repository for this project, and after that we are going to go through the specific details of how the language will look like, what the language will look like. So this is the repository. Yeah, that's it. This is what I'm using to record myself. It's ffmpeg with this command. So now that I have the repository, I'm going to pull and synchronize with this GitHub repository locally. Oh yeah, I forgot something. With SSHFS, the repository, if I mount it like this, I'm going to have a problem with file permissions. If I touch a file, what? Oh yeah, so here you can see that the file ownership is not correctly set because my user on my local computer does not have the same ID as my user on my VPS. So to fix this, I'm going to unmount the SSHFS, and I'm going to remount it with the correct user ID and also the correct group ID. So now the files have the correct IDs. So if I don't use these options, the file permissions will be handled by the kernel, and the kernel doesn't know that there is an SSH connection that is mapping the remote files. And with these parameters, the ID commands that give me my user ID, group ID, and everything, I will tell SSHFS to use the correct to show the correct file permissions, because the SSHFS I'm using is actually correct. The file permissions are actually correct, since SSHFS is using my username on the server, and I'm using the user's account, this user's account, to edit the files. So I just have to tell the SSHFS to show the correct file permissions. So now I can go to the project directory, and I can set up the remote origin. The Git calls are slow because SSHFS requires pulling all the files every time Git tries to read a file. So this is much faster if I just do it here. But here I don't know if I have. Yeah, I have my Git key. Okay, so I can use Git to push and pull from here. And since I don't have anything in the repository, it's not working, I guess. So I'm going to add the test file. Yeah. This is the basic Git configuration to report the correct this is a configuration that is needed for every project. So this time it's working, and I can do git status from my local computer, but I won't do it because it's too slow. So now I'm going to explain what are my plans with this project. So the reason why I started to write a Lisp interpreter, a Lisp project, which it's not the first time I do it, but this time I'm trying to implement a Lisp that can be used to access to transpile to other languages, and I want this Lisp to be usable by AI, so that AI can help me write in a language that can compile to every other language. There is no guarantee that it can work, but yeah, it's fun. So the first characteristic is that the Lisp is interpreted. This is a Lisp that is not going to run by itself. It's going to be used to generate programs in other languages. So for example, if I want to write a website with it, instead of using the Lisp web server that will run a Lisp function to generate HTML, this is an example of a common Lisp function that would be used to generate HTML. Instead, I'm going to use this language, this Lisp, to generate a script that will generate a web server and write it to a file. And this script will output the HTML. It's not a good example. So let's say, for example, I want to write embedded software. I can write it in C. I could probably write it in Rust. I can't write it in Python. I also can't write it in Common Lisp, because Common Lisp is probably, well, it could be as fast as the other languages in some contexts, but what I'm trying to do instead is to use Lisp to write a C program that will run in embedded contexts, in an embedded environment. So that's why I'm going to write an interpreted Lisp instead of a compiled Lisp, because I think it's going to be much simpler than an actual compiler. And for Lisp implementations, in my experience, it's also much simpler to implement a Lisp interpreter than a Lisp compiler, because writing a Lisp compiler and running macros requires having a Lisp interpreter inside the compiler. So to save some efforts and reuse code, I'm going to write an interpreter. The other choice I'm making is that the Lisp interpreter itself, because this Lisp is used to transpile to other languages, the interpreter can be bootstrapped from this Lisp. So I'm going to write it in Python for now, because I'm used to it, but it should be bootstrappable in any other language, even Rust if you want, by simply transpiling to the interpreter itself to Rust. So I'm going to use Python for now, until it can be transpiled. And because I'm not a Lisp expert, I'm not going to implement existing Lisp standards like Common Lisp or Scheme. Instead, I'm going to write my own version of Lisp, because I don't master all the abstractions that all the Lisp standards have. I know some of them. I am more used to Common Lisp, and I'm going to use the tools that I know how to use. So, for example, I'm going to use quasi-quotes, this feature. This is a Common Lisp syntax that is used for metaprogramming. I'm not going to implement reader macros, so it's going to be written this way. And so it's not a Common Lisp or a Scheme, it's a custom Lisp, and I'm going to try to make it minimalist, so that ideally even existing ChatGPT models could bootstrap it by themselves, or convert it to, or write their own implementations. So at least for the beginning, I'm going to use Python, because I'm reusing the dynamic features of Python, like the garbage collector, dynamic typing system, and things like that. But also because I want the core of this Lisp to be very small and very easy to understand. That way you can also read it and make your own Lisp later. And I'm not going to implement reader macros. The reason for that is that reader macros have specific requirements for what did I do? Okay. So, okay. I'm using them. That's why I'm failing everything. So, reader macros have specific requirements on how the language is implemented. For example, the read function, which is a recursive function that can parse Lisp values out of text. I'm not going to specify how this function is supposed to work, and I'm not going to rely on the way it works to implement reader macros. I think this is going to be having a minimal standard or minimal specification is going to make it much simpler for an AI model to modify the runtime, the interpreter, and add new features when needed. So the Lisp runtime itself should be adaptable to the project. So I already have an existing Lisp implementation, which I called OpenLisp, but the project is already there. It's not finished, but it's the only parts I need to finish are the tests for built-ins and you see I have a lot of tests that are not written, and some of these functions are also not implemented, and the macro expansion and quasi-quote is not implemented, but this is basically the third iteration of this project, so I don't think I will have I don't think I will have many setbacks while doing it, and things should be maybe too quick for someone who doesn't know how a Lisp is interpreted, but because I'm starting with my pre-existing knowledge, but it shouldn't be too complicated to understand, I hope. The only hard part is understand how to make it simple, I think. So I'm going to start with the parsing algorithm. So the parsing algorithm can be done in many different ways. There are parser combinators that can be used for it. There's a recursive descent. Hopefully I'm going to explain all of them. And I think it's... well, that's all I'm going to use. I'm going to add the tokenizer, and I'm going to try to implement another technique that I found in compilers, but I don't remember its name. So the idea is to map every parsing step, every compilation step with the previous input. For example, if I write a function, a compiler will parse the text of the function, transform it to statements and syntax elements that can be transformed into an abstract syntax tree, and then the compiler will create a function in the output language or the binary or in binary executable format. But the idea that I'm going to try to implement is to map the result with the beginning. So if I look at a binary function compiled from a C program, I'm going to have specific access to specific information about which place in the source code matches with this function, and what parts of the abstract syntax tree are on this function specifically. So this feature is going to be useful for implementing debugging messages, because currently I don't have any. I need to print the values and inspect the state of the program instead of having good stack traces. So I'm going to try to implement this feature. About the tokenizer, the tokenization is a process where I take the source code and I generate a list of tokens. These tokens can be any keyword or syntax elements that make up the program. For example, if I have this source code, the job of the tokenizer is to transform it into this. So the tokenizer is going to identify which parts of the program are independent from each other, and it's going to make the next steps easier. The tokenizer is not needed, would not be needed if I used parser combinators, but I'm going to use a recursive descent parser, which really needs a tokenizer to simplify. So next is the parser combinators. So the parser combinators is an approach to parsing where I have, for example, a parsing function which will take source code as an input and generate something, and another source code. So let's say I have this source code. This function will output a character and the rest of the program. This is a basic parser. It doesn't do anything. It just takes a part of the program, a character, and returns it and removes it from the source code. With parser combinators, we use combinators, which are functions that transform or combine the parsing functions. So for example, I can define an operator, a function that will concatenate the results of two parsers. In this case, I'm going to concatenate two character parsers, and I'm going to generate a new parser that takes source code as its input and generates something, not necessarily a string, and more source code. I'm going to use AI to write faster. So in this function, I'm going to apply the first parser, take the result and the source code left, call the second parser and the source code left, and take the second result and the source code left, and I'm going to return this value as a result, and the source code left after both of them have been executed. So now if I want to parse two characters, I just have to do that. And if I run it, I'm going to have this as a result, theoretically, if I don't have bugs. I'm not going to use parser combinators here. Parser combinators are a very easy way to write complex parsers, but they need to be able to go through the entire code before returning. In Lisp parsers, usually the parser used is a recursive descent parser, which is a recursive function, and it's more low level than parser combinators, but it can be incremental. For example, if I want to parse a program, I'm going to write a parser that will do something and parse the entire file, or parse an entire function declaration. But what I would like to do instead is to use programs that will only return one value at a time. Well, actually, parser combinators could also be used for incremental parsing, but my existing code, I think it uses incremental. Yeah, it's incremental. No, it's not. Okay, so I don't know. I think I'm going to so I'm going to use the recursive descent parser because it requires less code. That's the real reason. With parser combinators, I will need many parser combinators, like a parser that will execute the same parser many times. And with recursive descent, I can just tokenize and that's it. Because if I want, for example, to parse integers with the parser combinators, I would have to write it as something like this, and this as so, for example, if I wanted to implement an integer parser, I would have to implement a parser filter, which creates a new parser with a filter embedded in the parser, and an integer parser, which would then apply the digit parser many times, and it's too complex. It takes a lot of time to get each parser right. It's very easy to have bugs in the parsers. For example, an integer is easy to parse, but if I want to parse this syntax, I'm going to have to put in a lot of work just to describe what a value can be, and maybe that's what I'm going to use in the end, but for now I don't want to take too much time writing a parser. This is the previous parsing code. It's 100 lines. It's much simpler than a parser combinator library. So there is a token parsing part. This is the most complex part, I think, because it's a state machine. I don't like state machines. It's too verbose, but it does the job. This function is it is the read function is the Lisp read function, which works on tokens instead of using it uses tokens to tokenize the program. The tokenization is incremental, I think. So yeah, there is only one token parsed at a time, and the tokenizer returns the size of the token, and the read function will take tokens as long as needed and create recursive expressions. That's where the recursive that's where the recursion is used. Here. So the recursive descent algorithm is when I have a function which takes source code as a parameter, for example, or tokens, and if I have a recursive code, like for example I have a JavaScript code like this, if I start to nest functions, every level of indentation is going to match a level of recursion in the parser. So if I have, let's say I have 5 levels of nesting, then my function is going to have 2 or 3 levels of recursions, and I can have 200 levels of recursions without any risk of crashing the computer, the program, because a sane program doesn't have 200 levels of indentation or 1,000 levels of indentation. So I'm going to use recursive descent as a parsing algorithm, and I don't want to copy my old code as it is, because that would be cheating. I'm going to try to implement it from scratch, even if I already know how it works. Before the tokenizer, I want to add another step, which is the source mapping. Let's do it that way. So this is about mapping compilation steps with the source code. So this step will take characters and map them to line positions and line numbers. I'm not sure how to do it with the tokenizer without reading the entire file. So for now, let's say I'm going to be completely inefficient. I'm going to parse the entire source code and create a value for each character in the source code. Instead of having a string, I'm going to have a list of tuples. So for each character in the source code, I'm going to get the line number and the position on the line before returning it. First line, position 1. Let's say I'm going to use a class to represent characters. Okay. That's it. So I'm going to, for each character, yeah, no, it's clearly not correct. So for each character, I'm going to add its position and on the line it is, and the line number before returning it. And then I'm going to increment the counter, or if it's a new line, I'm going to increment the line counter and reset the position, the index on the line. That's it. So let's say I'm going to have a test source directory with some text, and I'm going to map the test code file. So to run it, I'm going to be on the server. I could write some unit tests in order to automate regression detection to avoid bugs, but I don't think the program is large enough for that now. So, oh yeah, I need to add a project print function. This isn't better. Yeah. So now I have what? Oh yeah, sorry. So this function is not correct because every new line character is printed as a new line, which is not what I want. So I'm going to use rep on the new line characters to represent them in as Python values. So this is the first another fix. Sorry. So right. Yeah. So The first character is a new line, this is correct. The second character is also a new line, and then on the third line the first character is a parenthesis, and then print, you can recognize it here, space, a string hello world, string, and closing parenthesis, and more new lines, with the last character being at in the 6 here, with the last character being on the 5th line after the 6. This seems okay. Now that the source line, now that the line counter is working, I'm going to write the tokenizer. So the tokenizer is not going to use a string, it's going to use a list of character with additional metadata. This typing notation requires the typing module. And the function is going to return a list of tokens. It's going to go through the entire file and not stop at a single token. So to parse the tokens, I'm going to write a new class for tokens with the source mapped metadata. I'm thinking about how to code it. If I used parser combinators, it would have been much easier because it's more verbose, but the parser combinators are doing all the work by themselves. For example, the value, the line counting is going to be embedded inside the parser combinators. I forgot how to write the tokenizer. So I'm going to start with this, with the for loop. Since I'm going to tokenize all the source in one go, in one pass, I'm going to simply append them to the list. The tokenizer is going to use the state machine. So if you don't know what a state machine is, in theory, a state machine is when you have an automata, a program that has a state, and I don't know how to explain it. So a state machine is usually studied like this. It's used in embedded software, for example, to program things like blinders. And for each state the program can be in, the program can receive events that will change its state. For example, if this is the current state of the program, this event will push it to this state, and then it can go to this state and other states. there is usually a beginning to the state machine, an initial state, and sometimes a final state where the machine stops. Maybe I can find an example. Yes, this is this one. So this is the initial state. This is what the program starts with, and with the first event, it's going to start doing its work, and it can finish in two different states, for example. So if I want to do it with a Python function, I'm going to need to store the current state. For example, I could have a string parsing state. If my parser is currently trying to parse a string, and it's a brute force process. So if the current state is the default state, which is when it's waiting for an input, I'm going to test the different possibilities. For example, if it's the beginning of a parenthesis expression, then I'm going to add to the tokens a new token. So on this code that an AI wrote for me, a token is made up of a type, a value, and a line and a position. I'm going to use this for the parenthesis tokens, this type, the syntax type, because it's a part of the it's what is used to well, it is the syntax of the language. It's a Lisp, so the only syntax that exists is parenthesis. And I'm going to brute force all the cases that exist. In the initial parsing state, so if my tokenizer is here, for example, new lines or white spaces are completely ignored. So if my program if my tokenizer goes on white space, it's in the initial default state, it's going to ignore it. Same for new line characters. New line characters are ignored. And then we have the values. So if it's no, not this. So if the character is a digit, I'm going to change the state, because we are now trying to parse a number. So the state is going to be number, and I'm going to add a buffer. Yeah. No, it's going to be a list of characters. So instead of trying to add a new token, I'm going to wait to see how long the number is before adding it into a new token. So I'm going to add the character to a buffer. The character with the line and position that was found before. If we didn't find the number, but instead an alphanumeric symbol, a symbol is something like this, a variable name, I'm going to change the state to symbol parsing, and I'm going to use the buffer for the symbol characters. And if something else happens, I don't know. So I'm going to wait until this case happens. maybe I forgot a state. So it's important that for every state machine there is something that is that will report unknown states, unknown situations, to make sure that everything is fine. For example, if I'm using characters like this, or Greek letters, for example, in my symbol, Lisp is going to treat this as a correct symbol. This is the correct variable name in Lisp. So to take this into account, I'm going to say that everything that's not a parenthesis, a white space, or a number is a symbol character. So if I start writing some weird hieroglyphs, my interpreter is going to treat this as a variable name. The next thing I'm going is to treat the number parsing situation. So if I'm going to find new digits, I will add them to the buffer. If we didn't find a digit, then there is a problem, because what did we find? So if it's I'm not going to take floats into account for now. If the character is a new parenthesis, open or closing, I spend more time deleting the suggestions. Then I will have to add this code is wrong. So at this point I need to join the buffer. I also need to create a token with a number, with the correct number, but also I need to remember the line, the beginning position and the end position. So start line, start position, end line, end position, and I'm going to rewrite this. Yeah. So now that I have all these parameters, I can say, for example, that this number goes from the first character on the fifth line to the last character on the fifth line. And that's what I want to be able to do at every step of the compilation or the interpreter. So in order to do that, I will need auxiliary functions that will get the first position in the buffer. Yeah, and same for the inline and position. I'm going to use the last element in the buffer. To join the characters in the buffer, I'm going to do this. I know there are many bugs in this program. I'm convinced there is no way this is going to to work for the first time. So this, okay. I'm going to open the token, and I'm also going to do how to say it. So there are two ways of doing this. So either I add a rollback condition where I can go back from one character with an index, for example, or I can copy paste this code here. I prefer having a rollback because it uses less repetition, and state machines are already very repetitive. So with this I can just decrement I and go back from one character. And set the state back to default. And now I can also add this and this. So if I have any of these characters, I'm going to go back here to go back to the previous position and treat them as if there was no number parsing before, because the number parser has finished. And if I have another character, this time it's going to be an error, because if I write something like this, I'm sorry, but this is incorrect. I can't. I don't want to have this working in my language. This really shouldn't happen. So I'm going to raise an exception if the code has this. After the language is more complete, I'm going to add error handling. And at this point, the good part is that with the character having metadata, I can report the error and say exactly where in the file this error happened. Just with this. So if I have this error happening, because of the source mapping that I set up here, I will have access to the exact line and position of the error, which wouldn't be the case if I didn't do this part and started with the tokenizer. And this is pretty long already. I'm going to add the last state for now, because there is also the string handling which is not done currently. For the symbols, we already decided that any character is okay. So instead of trying to test if it's an alpha number, I'm going to test if it's a special character. If so, then we are going to do this. And this. I think there is a problem here, because I didn't. Oh no, it's okay. It's not a problem, I think. So here I'm going to finish the token. This is not a number, it's a symbol. And token is appended to the token list. Oh, I remember what I forgot. This. So every time the buffer is finished, every time I use the contents of the buffer, I have to reset its contents so that I can use it again for anything else to parse. So if you look at it from a state machine perspective, this is part of the state, and this is it can be considered part of the state, but it doesn't really interfere with the state machine. But the buffer is a part of the state. So if I wanted to draw this as a state machine, it would not be possible, because every possible combination in the buffer is a different state. Or I could have, or I could describe the state machine as a combination of multiple state machines, but it's not a simple standard state machine that can be represented as a graphic. And I think it's complete. So after the end of the loop, I can return the tokens, and if I try it, so this one, for example, is one of the things I forgot. Syntax warning. I didn't even know Python had syntax warnings. Is in. That's why it didn't work. So the tokenizer has recognized an opening parenthesis, the print symbol, and then we have another problem. There is no string. So it's recognizing the first quotes and hello as a single symbol, which is correct if there is no string. The quote symbol can be used as part of a symbol. The quote character can be used as a part of a symbol. Same for world quotes. And then there is a closing parenthesis, and then there is a number. So now we have to add a string parser. It's here, and I'm going to add another. Oh no. Yeah. So I need another state parser. I don't know what I'm typing, but I hope it's correct. Okay, so if I have the end of a string, I'm not going to roll back to a previous character. It's finished. if I have an end of quote, I'm going to include the to include this character in the buffer before closing the string. So the string will include I don't know. Yes, for now I'm going to do it that way. So the string is going to the quotes should not be included in the string. I'm not going to implement special characters like this. I'm just going to do a very basic string parsing with a quote, something, a quote. So when there is a second quote, I take the positions of the beginning and end of the character. No, I need this character. I need to include the string quotes inside the position of the string. So I'm going to add the quotes to the buffers so that I can take the positions, and then I'm going to remove the quotes from the buffer like so, and I don't know why it's always called number. It's also called number here. So this is going to add the string to the tokens, because the string is a single item in the abstract syntax tree. It's not something composed of other things, so it's read as an atomic element, which is a token. And I think it's going to work. Yes, it's working already. So I have the print symbol, and then I have the hello world string, and that's it. It's working. If I want to add the positions in the representation of the token, I can do it with this notation, for example. Yeah. So now I can see that this parenthesis is at the first character of the third line. The print symbol is from the second to the sixth character in the third line. The hello world string is from 8 to 20, and the closing parenthesis is at the end of the line, and the number is on the fifth line. So that's what we wanted to do with the source mapping. Now I can reuse these things to say, for example, that the third line from the first character to the 21st character is a single expression, which is the print call. So this is already 100 lines of code. This method of parsing code is very easy to understand and very easy to apply, but it's so verbose and so easy to forget edge cases that I wouldn't recommend it. It's too specific. If I want to add any single part to the syntax, for example, if I want to add floats, I'm going to have to add new states, not just number but also integers and floats or exponents or I don't know. And I'm going to have to fight with so many edge cases that it's much simpler to use parser combinators, even if parser combinators require more preparatory definitions for combinators. In the end, it's much easier than state machines, but because it's a simple tokenizer, I'm not going to add an entire parser combinator library. This is just the tokenizer. It's not a parser, it's just a function that will receive a list of characters and output a list of atomic elements in a program, an integer, a string, a parenthesis, a variable name, things that really cannot be split. It's not a parser, it's not going to have any recursion of or anything like that. But a state machine can be used to do this, and I really don't recommend it. Just a tokenizer requires 50 lines of state machines, and it's a single function. It's completely unreadable. So I really don't recommend using state machines. So I think I will stop here for today. I'm going to add the parse and the parser and the source example. And by the way, if you want to know how I write these types of characters, it's because I use a weird keyboard. It's not a standard keyboard. I don't even know all these bindings, but they exist. I don't even see the difference between the Greek V and V. I have many characters. Many useless characters. That's it. Let's stop for today. So if I go to the repository, the code has been uploaded. It should have been. No, it hasn't been. So now if I want to quit the project, I have to unmount the SSHFS, which I can do. Okay, probably because of some file input to IO that didn't finish, but when it finishes, I need to unmount it in order to just because I don't need it anymore, and to be able to mount something else instead. I'm sure this is fine.